Have you ever experienced a peculiar psychological moment where the world around you suddenly feels completely unreal? Where your own hands and feet, which you continue to sense, seem more like sophisticated technological prosthetics than actual body parts? Where even the faces of your closest relatives appear to carry an otherworldly falseness to them? This extraordinary psychological condition is formally known as derealization, and it represents a profoundly disorienting state of consciousness that many people experience at various points throughout their lives. Derealization manifests as a temporary alteration in how the brain processes and interprets sensory information about reality. During these episodes, time and space begin to feel distorted, stretching and compressing in ways that defy normal perception. The surrounding environment transforms into something that seems distant, strange, and dreamlike. According to research conducted in North America, the birthplace of one famous actor who portrayed a character experiencing precisely these symptoms in a 1999 film, nearly 1 million people encounter derealization episodes every single month. This means that if you have never personally experienced this condition, the probability remains high that you eventually will during your lifetime. The fascinating aspect of derealization lies in what it does not involve. During these episodes, individuals do not hear, see, or sense things that do not actually exist in reality. Rather, they perceive actual events and environments as though viewing them through virtual reality equipment, staring through glass, or watching a cinema screen. People experiencing derealization consistently report that what they observe feels devoid of brightness and emotional resonance. The visual information appears flat, lacking the normal vividness and color that reality typically presents. Most remarkably, people often report that their emotional responses to familiar environments, and even to faces of those they love, most profoundly become dramatically reduced or nearly eliminated. This condition frequently accompanies other unusual perceptual phenomena. Many individuals experiencing derealization report sensations of déjà vu, that distinctive feeling of having lived through an identical situation before, or of having witnessed events in dreams that now manifest in waking life. Interestingly, the opposite phenomenon also occurs frequently. Jamais vu describes the sudden sensation that well-known places become completely unfamiliar, or that people you have known your entire life appear strange and unrecognizable, as though you perceive them for the first time. In some individuals, these jamais vu episodes can trigger panic attacks so severe that they warrant medical attention. Yet despite how terrifying these experiences feel, the condition typically resolves naturally within hours or days. Chronic derealization remains comparatively rare in the population, affecting only a minority of those who experience occasional episodes. The remarkable parallel between derealization symptoms and a particular narrative in popular culture became impossible to ignore. A character in a 1999 film experiences precisely these symptoms, the unexplainable certainty that reality itself is fundamentally false. Yet in that story, the character's perception proves accurate. His world actually is artificial. He lives within a simulation created by machines and connected to an elaborate virtual reality. His entire universe represents manufactured illusion. The concept of simulated worlds predates modern cinema by decades. In 1964, an author published a novel that stands among the earliest literary explorations of virtual reality concepts. This novel, which later inspired a film released in 1999, contained remarkable prescience regarding technology and consciousness. The film adaptation featured an extraordinarily memorable sequence that illustrated the consequences of existing within artificial reality. In this scene, the protagonist character travels to what appears to be the literal edge of existence, where the digital world has not been fully rendered. Beyond this boundary, reality appears as nothing but a primitive wireframe model, visible structures but no textures, colors, or details. The experience horrifies the character, who witnesses this evidence of artificiality. Despite this earlier film being quite well crafted, the enormous success of another major release from 1999 completely overshadowed it. This second film achieved such explosive cultural penetration that most people remain unaware of the earlier work's existence even today. The first film presented simulation concepts cinematically, yet the second film created something far more significant, a genuine cultural phenomenon that would reshape how billions of people contemplate reality itself. The statistics regarding this second film proved truly remarkable. On the world's largest database of cinema containing information about more than 700,000 motion pictures and visited by 500 million individuals monthly, this film ranks at position 16. Among 700,000 films, it occupies the 16th position. This ranking does not derive primarily from innovative special effects or exciting action sequences, though the film certainly contains both. Rather, the film achieved this ranking because it touched something profound within human consciousness itself. Before 1999, the vast majority of humanity had never seriously contemplated simulation hypothesis. No major popular works had explored this concept. Yet this single film entered culture and struck such a powerful nerve that it permanently altered collective human consciousness. It became the reference point for an idea that apparently had always existed at the periphery of human thought, waiting for someone to articulate it clearly. The film succeeded in making explicit what had remained implicit in humanity's deepest wondering about the nature of existence. The lasting cultural impact proves extraordinary. More than 2 decades after the film's release, video creators continue analyzing its philosophical implications at lengths exceeding 20 minutes. These analysis videos consistently rank among the most viewed content on major video platforms. The author of one particularly influential philosophical paper, published in 2001, became so identified with simulation hypothesis discussions that nearly every single video addressing this topic references that paper. The speaker claims he has never encountered another philosophy paper cited with such frequency across popular media. The pervasiveness of simulation hypothesis discussions has reached a point where some individuals report intellectual exhaustion from the topic itself. The idea has become so ubiquitous, so thoroughly woven into popular culture, that it seems impossible to escape. Yet this very ubiquity suggests something important. If hundreds of millions of minds find themselves drawn to this concept, if content addressing it dominates video platforms, if some of the wealthiest individuals on Earth have reportedly invested billions in secret research, attempting to understand whether this hypothesis might be true, then perhaps the hypothesis itself deserves serious consideration. To properly evaluate whether we might inhabit a computer-generated simulation, we must first consider how inhabitants of such a simulated world could detect their artificial environment. Let us imagine that all humanity existed as conscious beings within a sophisticated video game that attempts to simulate our universe. What would be our first logical approach to discovering the truth about our existence? The most intuitive approach would involve searching for the simulation's boundaries. If the simulated universe has finite extent, then traveling far enough in any direction should eventually encounter an edge, a point beyond which the world ceases to exist. This represents how one might test the hypothesis, locate the simulation's border. In one particularly well-known 3-dimensional video game environment, the explorable game map measures approximately 6 kilometers by 6 kilometers. The terrain consists of cities, countryside, water, and sky, rendered with great detail. One might reasonably hypothesize that if one could somehow obtain the fastest available vehicle, travel at maximum speed, and journey far beyond established civilization boundaries, eventually one would encounter the simulation's edge. Perhaps this edge would appear as an invisible wall, or perhaps as the point where the game engine ceased rendering new terrain, displaying instead a void or primitive geometric shapes. However, the game designers demonstrated considerable sophistication in their approach to this problem. Should a player attempt to travel beyond established map boundaries, they discover something unexpected. No actual wall exists. The ocean surrounding the map simply continues infinitely. A player can travel outward indefinitely without encountering any barrier. The game engine employs clever programming to prevent the player from ever actually reaching an artificial boundary. Instead, the character begins gradually losing health through starvation as they travel farther and farther from civilization and food sources. Nevertheless, the game designers implemented additional safeguards. Should a player somehow circumvent the starvation limitation through game modifications and continue traveling uninterrupted for 3 continuous months of real-world time, they would eventually traverse approximately 300,000 kilometers of game world distance. This distance equals the space between Earth and the Moon. At such extreme ranges, the game engine begins to experience computational difficulties. The character's physics model breaks down catastrophically. The character begins to fragment and blur, spreading across the virtual space in grotesque and impossible ways. This glitch represents a fascinating concept. Should a simulated character observe this phenomenon through binoculars from a distance, how would they interpret such chaos? We could not yet claim definitive proof of simulation. However, this glitch would represent the first tangible evidence that something remains profoundly incorrect with their perceived reality. They would possess their first coin in the jar of suspicious observations. Now consider our actual universe in this context. The equivalent of infinite oceans surrounding a video game map would be outer space itself. If humanity could somehow develop technology enabling an individual to travel arbitrarily far from Earth via spacecraft, traveling in a straight line away from our planet for an indefinite duration, what peculiar anomaly might they eventually encounter? According to certain theoretical physicists, they would eventually discover an anomaly that raises the most serious possible questions about the fundamental nature of reality itself. To properly understand the anomaly potentially awaiting us at the universe's boundary, we must first examine the strange properties of black holes through the theoretical framework established by one of the most influential theoretical physicists of our age, a pioneer of string theory, a holder of numerous prestigious scientific awards, and an author of popular physics books that have introduced millions to advanced concepts. His analysis of black holes opens doorways to understanding our universe's most perplexing features. Imagine an astronaut piloting a spacecraft directly toward an enormous black hole. General relativity and Einstein's revolutionary theories describe what happens as this astronaut approaches the event horizon, the theoretical boundary surrounding the black hole beyond which escape becomes physically impossible, where no object, regardless of velocity, can ever return to the outside universe. What precisely does this astronaut experience as they approach this ultimate boundary? General relativity provides an elegant and seemingly counterintuitive answer. At the moment of crossing the event horizon, absolutely nothing catastrophic occurs. The astronaut experiences no sudden jolt, no sudden forces, no warning signs of danger. They perceive only ordinary weightlessness, the standard sensation one experiences in open space far from any planet or star. Any astronaut who has floated freely in the vacuum of space knows this sensation. From the astronaut's perspective, crossing the event horizon differs not one iota from traveling through ordinary empty space. This peaceful passage creates a genuine paradox of understanding. The actual danger emerges much later, hours, days, or even weeks of continued falling, depending on the black hole's size and mass. As the astronaut falls closer toward the black hole's center, gravitational forces gradually increase. Tidal forces, differential gravitational acceleration between the astronaut's head and feet, eventually become strong enough to stretch the astronaut across space in an agonizing process. Eventually, near the black hole's singularity, these tidal forces would shred any material object to subatomic particles. However, at the precise moment of event horizon crossing, the astronaut experiences none of this. They pass unharmed through the point of no return. Yet when an external observer stationed safely distant from the black hole views this same scenario through a powerful telescope, they observe something entirely different. The external observer would witness the approaching astronaut moving progressively slower. With each passing minute, the astronaut's movement would decelerate noticeably. This deceleration would continue without end, as the temporal dilation effect near black holes causes time itself to pass more slowly relative to distant observers. The astronaut would never be observed crossing the event horizon. Instead, from the external observer's perspective, the astronaut would appear to freeze in position, becoming increasingly difficult to perceive as light from the astronaut becomes progressively redshifted toward infrared and radio wavelengths. Up to this point, the situation remains comprehensible through standard relativity. However, theoretical physics proposes something far more disturbing and philosophically troubling occurs. According to frameworks developed by contemporary theoretical physicists, when the distant observer looks toward the event horizon with sufficiently sensitive instruments, they would observe something genuinely terrifying. The approaching astronaut would appear to collide with what represents possibly the deadliest structure in the entire universe, a firewall of unimaginable intensity. This phenomenon, termed a firewall or black hole firewall, manifests as a surface of incredibly energetic particles and radiation generated by processes related to Hawking radiation, the theoretical radiation that black holes emit due to quantum effects near event horizons. The temperature of this firewall approaches infinity, possessing energy sufficient to instantly incinerate any object contacting it. From the external observer's perspective, the astronaut experiences a death of incomprehensible violence, vaporized in an instant within a corona of flame surrounding the event horizon. This situation creates an impossible paradox. Two perspectives exist regarding a single event. From the astronaut's viewpoint, the reference frame of the falling observer, they pass uneventfully through the event horizon, experiencing no pain, no barrier, no impediment to their passage. Absolutely nothing prevents their safe transition. Yet from the external observer's viewpoint, the astronaut dies in catastrophic fashion within seconds, incinerated by the black hole's firewall. How can both statements be true? How can the same person simultaneously experience peaceful passage and violent death? The same individual cannot possibly exist in two contradictory states, yet contemporary physics insists both perspectives represent valid descriptions of reality. This apparent contradiction should not occur, yet the mathematics of relativity combined with quantum mechanics produces exactly this situation. The resolution of this black hole paradox has led theoretical physicists to propose a revolutionary notion. The three-dimensional universe we perceive and experience might represent merely a holographic projection. According to this framework, information about everything occurring within a bounded region of space can be completely described using information located exclusively on that region's perimeter, specifically on its two-dimensional boundary surface. This principle emerged from research into black hole thermodynamics and information theory. The black hole paradox demonstrates that the concepts of space, time, and dimensionality that we consider fundamental might not be truly fundamental at all. Perhaps space itself represents an emergent property derived from more basic information structures. Perhaps the three dimensions we experience constitute a kind of holographic image projected from two-dimensional information. To understand the profound implications, consider how our universe actually expands. Observations and theoretical models indicate that the universe approximately doubles in size every 15 billion years. This expansion occurs uniformly in all directions. As a consequence, in all directions from Earth, at approximately 15 billion light-years distance, observers encounter what appears to be a cosmic event horizon, a boundary similar in character to the event horizon surrounding black holes. Beyond this cosmic boundary, objects recede from us faster than light travels. This faster-than-light recession occurs not because objects move faster than light through space, but because the space itself expands continuously. As space expands, the distance between us and distant objects increases at rates that exceed light speed. Critically, signals traveling at light speed cannot bridge the expanding gap. Objects beyond our cosmic horizon can never communicate with us. No light, radio signal, or any other form of information can ever reach us from beyond that boundary. This creates a profound situation. Each observer, each conscious being, finds themselves surrounded by their own personal cosmic horizon. Just as you exist at the center of your personal viewpoint, so too do you exist at the center of your personal event horizon. Every direction you look, approximately 15 billion light-years outward, your cosmic horizon consumes galaxies, stars, and potentially even existing civilizations. From your perspective, you inhabit your own private, personalized black hole inverted inside out. This similarity between personal cosmic horizons and black hole event horizons extends to precise mathematical descriptions and physical consequences. As objects approach one's personal cosmic horizon, they appear to decelerate progressively, mirroring exactly what occurs with black holes. The temperature of spacetime would increase as objects approach the cosmic horizon, eventually reaching infinitely high temperatures at the boundary itself. Objects at the cosmic horizon would be subject to forces and temperatures comparable to those at a black hole's event horizon. The mathematics describing this situation applies equally at both the cosmic boundary and at black hole boundaries. This symmetry cannot represent mere coincidence. The same physics operates at both locations. Therefore, if the solution to the black hole paradox involves encoding information on a two-dimensional boundary surface, then perhaps the same solution applies at cosmic scales. Perhaps all information about our entire universe, every star, every planet, every atom, every particle, every human being, is actually encoded as information existing on the two-dimensional cosmic boundary 15 billion light-years away. This holographic principle, while initially shocking, has become an active area of research among theoretical physicists working on string theory, quantum gravity, and fundamental physics. It is not a marginal hypothesis entertained only by fringe thinkers. Rather, it represents seriously pursued theoretical research at prestigious institutions. One remarkable physicist shaped nearly every major development in 20th century physics. He collaborated with Niels Bohr, contributed to the Manhattan Project, mentored extraordinarily talented physicists who developed revolutionary theories, and his name became synonymous with black holes themselves. This individual was John Archibald Wheeler. Toward the end of his life, during a lunch conversation at Princeton, he was asked a profound question. What did he believe would become the dominant theme of physics over coming decades? Wheeler paused for a long time, as if considering carefully before answering. Then he lifted his gaze and spoke a single word: information. This physicist had become convinced that information represents something more fundamental than matter and energy. Objects, matter, radiation, and all familiar physical substances should be considered secondary phenomena. These are merely carriers of something far more abstract and far more basic: information itself. From this perspective, the core of reality does not consist of quarks, electrons, photons, or any material substance. Instead, the core of reality consists of bits of information, abstract data describing properties, locations, states, and relationships. Information, according to this framework, represents the true substrate of existence. That information describes which particles exist, where they are located, what their quantum properties are, whether their electric charges are positive or negative, what their spins equal, and countless other characteristics. The universe, viewed through this lens, functions as an information processor, rather than as a collection of material objects floating through space. This perspective resonates with contemporary theoretical approaches to fundamental physics. Multiple prominent theoretical physicists now maintain serious interest in whether the universe itself might function as a vast computational system. Some researchers propose that the universe operates like a cellular automaton, a system in which simple algorithms applied uniformly throughout space generate all the complex phenomena we observe. Others suggest that the cosmos functions like a computer program, executing on some computational substrate. Still others maintain seriously open positions regarding simulation hypothesis. A particularly renowned contemporary theoretical physicist and string theorist authored an influential book examining hidden aspects of reality. In this work, he devoted nearly an entire chapter to exploring simulation hypothesis from a scientific perspective. This represented unexpected attention from such a prominent figure, one of the most publicly recognized theoretical physicists of our time. Given that such a prominent figure would devote substantial written space to this topic, others took notice. The author subsequently discovered that enormous numbers of scientists working across various disciplines remain intellectually willing to seriously entertain the possibility that the universe functions as a computational system. This represents not mere philosophical musing, but genuine scientific inquiry into fundamental reality's nature. The logical foundation supporting this inquiry becomes clearer when one recognizes that if information truly forms the bedrock of physical reality, then the distinction between a real universe and a simulated universe becomes philosophically murky. If reality consists fundamentally of information and information processes, then whether that information processes occurs within what we call physical hardware or within what we call computational hardware becomes a distinction without a difference. In both cases, reality consists of information and its transformation. In both cases, observers like ourselves experience that information through sensory mechanisms and consciousness. A fundamental principle governing the nature of physical law in our universe can be termed the Turing principle. This principle states that the physical laws governing our universe permit, indeed enable, the construction of physical objects capable of simulating any portion of our universe with arbitrary precision. Every personal computer, every smartphone, every laptop computer represents exactly such a Turing-capable object. When one truly contemplates this principle, its implications prove genuinely profound and non-obvious. There exists no logical necessity that physical laws should permit universal simulation. Many might intuitively expect that fundamental physics would prohibit the possibility of comprehensive universe simulation. One might anticipate that some limitation in the laws of nature would prevent the creation of sophisticated simulations. Yet empirically, through observation and experimentation, we confirm that simulation of universe portions absolutely remains possible. Consider a popular video game released in 2016. The developers simulated a universe region containing 255 galaxies. The total number of planets within these galaxies reached an astronomical figure, 18 quintillion planets. More precisely, approximately 18.5 quintillion individual worlds. Each planet within the simulation possessed entirely unique geography, different landforms, different climate systems, different arrangements of continents and oceans. Each world contained unique flora and fauna, different species of plants and animals adapted to each world's unique conditions. This represents an extraordinary feat of computation. Yet, for someone to personally examine all this content would require incomprehensible duration. If one visited one single planet per second, continuously, without rest, examining each world would require 585 billion years. This duration exceeds the universe's current age by a factor of 42, yet the simulation contained this entire universe region, all 255 galaxies with all 18 quintillion worlds, within a computer program that could operate on consumer-grade personal computers. Yet the significance of the Turing principle extends far beyond entertainment applications or video games. If this principle did not hold, if the laws of physics forbade comprehensive simulation, then multiple consequences would follow. First, computers would not exist. Second, and more profoundly, thinking beings like ourselves could not exist. The reason lies in how conscious beings function. When humans observe objects or contemplate ideas, we literally construct virtual models within our brains. These are not metaphorical simulations, but actual neural models. When one imagines a familiar building, part of one's brain representing spatial reasoning literally simulates that building's layout, appearance, and characteristics. When one visually imagines a friend's face, neural systems create a simulation of that face within consciousness. Einstein, when developing revolutionary physics theories, did not primarily use mathematical notation or laboratory experiments. Rather, he physically modeled experiments within his consciousness, imagining scenarios and working through their implications mentally before ever putting pencil to paper. Furthermore, this principle proves absolutely essential for the existence of life itself. Genetic material, DNA and RNA, fundamentally encodes information about the environment from which organisms evolved. Genes represent billions of years of environmental information compressed into molecular structures. By examining a single DNA molecule, a trained biologist can deduce substantial information about the environment from which that organism originated. An organism's genetics literally simulates its ancestral environments. This genetic simulation enables life to adapt and evolve. Life itself, from this perspective, represents the mechanism by which virtual reality was first realized in nature. Before computers existed, life was already creating simulations, environmental models within DNA, behavioral simulations within brains, prediction simulations within nervous systems. Among the most profoundly strange aspects of quantum mechanics lies an experimental finding that challenges basic intuitions about reality. A classic experiment, repeated countless times in laboratories worldwide, demonstrates that conscious observation fundamentally shapes the behavior of physical matter at quantum scales. This phenomenon, far from being a minor technical detail, strikes at the heart of what reality might mean. In the famous double-slit experiment, a stream of individual photons travels toward a barrier containing two openings or slits. Researchers can choose to measure or not measure which slit each photon passes through. When researchers actively measure which slit the photon travels through, each photon behaves as a definite particle, passing through either the left slit or the right slit, and creating two distinct bands of light on a detection screen positioned beyond the slits. Conversely, when researchers do not attempt to measure which slit the photon passes through, something radically different occurs. Instead of two distinct bands, researchers observe an interference pattern on the screen, a pattern of alternating bright and dark stripes. This interference pattern could only form if the photon somehow traveled through both slits simultaneously, creating a wave that interferes with itself. The photon behaves like a probability wave, existing in multiple states simultaneously. This is deeply strange. In the first scenario, with measurement, the photon is a particle. In the second scenario, without measurement, the photon is a wave. Same experiment, same photons, different outcomes based purely on whether observation occurs. This suggests that the act of observation does not merely register pre-existing facts about reality, but actually determines reality's behavior. The physicist John Wheeler proposed an even more extreme version of this experiment. Consider two extremely bright objects observed in the cores of distant galaxies, objects known as quasars. These two quasars lie 9 billion light-years distant from Earth. At first glance, they appear to be two separate objects, yet astrophysicists note they actually represent one object, viewed through a gravitational lens effect. Between this distant quasar and Earth, an enormous galaxy containing billions of stars is positioned. This galaxy possesses such tremendous mass that it curves space-time around itself, creating a gravitational lens effect. Light from the quasar traveling toward Earth can follow one of two paths around this intervening galaxy, either traveling along the left side or traveling along the right side. These two paths converge at Earth. A single quasar produces two images, visible in telescopes due to this lensing effect. Now Wheeler proposed something revolutionary: set up an experiment where one can measure which path the light traveled after the light has already reached Earth. One chooses whether to measure or not measure the photon's path after 9 billion years of travel have already occurred. If measurement equipment is active, the photons appear to have traveled definite paths, some along the left side and some along the right side, creating two distinct images. If measurement equipment remains inactive, something startling occurs. An interference pattern appears, as if the light traveled both paths simultaneously and interfered with itself. The critical paradox. The experimenter's choice, made in the present, determines which path the light took 9 billion years ago. Actions taken today retroactively determine events from the cosmic past. This phenomenon, called the Wheeler delayed choice experiment, has been conducted repeatedly in laboratories at smaller scales, always producing the same paradoxical results. The experiment conclusively demonstrates that at reality's most fundamental level, measurement does not simply register pre-existing conditions, but actively participates in determining reality. The observer becomes part of the observed system, not merely an outside recorder of facts. Through the lens of simulation hypothesis, this becomes readily explicable. A simulated universe with limited computational resources could render complete reality only when observation occurs. Unobserved regions might exist in a state of quantum superposition, multiple possibilities held simultaneously, rather than being fully rendered. This would drastically reduce computational requirements. Only when an observer looks at something would the simulation need to calculate and render those specific details into a definite state. If the universe actually operates as a simulation running on a computer with finite computational resources, then reality at sufficiently small scales must be discrete rather than continuous. Just as virtual reality headsets appear to display seamless, continuous graphics until examined closely, at which point one perceives distinct pixels arranged in a grid, perhaps reality itself consists of fundamental discrete units rather than infinitely divisible continuous space. Several contemporary theoretical physicists seriously maintain that reality is fundamentally discrete at its deepest levels. Research into quantum gravity suggests that space and time cannot be subdivided infinitely. Instead, they consist of finite units. The information capacity within any region of space is determined by Planck area units, areas defined by combining fundamental constants of physics. This suggests that space-time itself might possess a pixelated structure, with each pixel representing a Planck scale unit of space and time. This resolution of ancient paradoxes becomes clear when one accepts space-time discreteness. Centuries ago, an ancient Greek philosopher posed paradoxes about motion. One famous paradox involved a flying arrow. If time consists of individual, indivisible moments, then in each moment the arrow occupies a specific location and therefore must be stationary. Since the arrow is stationary in every moment, and since all of time consists of individual moments, the arrow must always be stationary. Yet we observe arrows in flight. How can motion exist if the arrow is stationary in each individual moment? If space-time consists of discrete, quantized chunks rather than continuous continuum, the paradox dissolves. Motion occurs through instantaneous jumps from one spatial location to an adjacent location. Between these quantum jumps, nothing occurs. No intermediate positions exist. No time passes. From the perspective of someone within the simulation, motion appears continuous because the discrete jumps happen at a rate so high that human perception cannot resolve individual steps. Just as cinema creates the illusion of continuous motion through displaying individual static frames at high speed, reality might create the illusion of continuous motion through displaying discrete spatial positions at the Planck scale rate. The speed of light represents the maximum velocity anything can achieve in the universe. This constant defines the cosmic speed limit. Every object, every photon, every particle travels at or below this speed. Yet remarkably, no fundamental physics derivation explains why this specific value exists. No known mechanism establishes that light travels at exactly 299,792,458 meters per second, rather than some other speed. No mathematical principle determines this value from first principles. This specific number simply appears in our physics equations. From the simulation hypothesis perspective, this limitation becomes readily explicable. The speed of light represents a fundamental computational limitation. A computer cannot perform infinite calculations per unit time. No matter how powerful, every computer has maximum processing speed. Similarly, a computer simulating our universe cannot process interactions faster than its hardware permits. Physical interactions and information transfer cannot exceed the simulation's processing speed limit. The speed of light limitation emerges naturally and necessarily from the finite computational speed of the host computer. Furthermore, Einstein's special relativity describes a phenomenon called Lorentz length contraction. As an object moves faster, space in the direction of its motion appears to contract. Distances shrink. This seems impossible to understand physically until reconsidered through a simulation lens. A fast-moving object requires more computational power to simulate accurately. The computer must calculate forces, accelerations, and interactions more frequently to properly model high-velocity motion. If total available processing remains constant across all particles and all regions of space, the computer might handle the increased computational load by reducing rendered space resolution in movement directions to conserve processing resources. Similarly, relativity describes time dilation. A clock on a fast-moving object appears to run slower than a stationary clock when observed from a distance. Again, this makes sense computationally. Maintaining precise simulations of high-velocity objects requires intense calculation. One method to reduce load might involve slowing temporal resolution for fast-moving objects, updating their positions less frequently, making their subjective time appear to pass more slowly. Perhaps the most genuinely profound mystery in all of science concerns the nature of consciousness itself. While neuroscience continues illuminating increasingly specific details about how brains function, the fundamental question of consciousness remains fundamentally mysterious. Why does subjective experience exist? How does the firing of neurons produce the felt sense of redness, the experience of pain, the sensation of emotions? This hard problem of consciousness remains stubbornly resistant to solution. Many contemporary scientists and philosophers notice an inverse relationship between understanding and mystery. As humanity comprehends physical laws with greater precision and depth, consciousness becomes increasingly mysterious rather than less. The more thoroughly we study the brain, the more elusive the essence of consciousness seems. Some philosophers propose that consciousness might represent something fundamentally non-physical, something that transcends the material realm and cannot be derived from or explained through physics. Others suggest that consciousness could theoretically be replicated computationally, but remains far too complex to reproduce with current technology. If consciousness could be simulated, the simulation would be extraordinarily complex and resource-intensive. Simulating even a single conscious being with complete psychological depth might require computational resources exceeding those necessary to simulate millions of unconscious beings. A particularly unsettling possibility emerges if consciousness simulation becomes technologically feasible at some future point. The universe possesses incomprehensible vastness. In an infinite cosmos, red dwarf stars shine steadily for trillions of years, durations far exceeding the current age of the universe. Solar energy from a red dwarf could power computing devices arranged through random occurrence around such a star. These computers could simulate complex universes containing billions of conscious beings. If, as theoretical calculations suggest, quantum computers could simulate millions of years of human subjective experience per second, then any beings within such simulations would experience suffering stretched across perceived eternities. These implications prove so disturbing that several philosophers have argued humanity should actively avoid attempting to determine whether we inhabit a simulation. The reasoning follows thus. If we succeeded in definitively proving our simulation status, the beings or civilization in the external reality who designed our simulation might consider their experimental model compromised. They might reason that once inhabitants become aware of simulation, they lose their authentic characteristics and behaviors. The simulation's validity, from the external perspective, depends fundamentally on inhabitants remaining unaware of their artificial nature. Discovery would render the simulation worthless for its intended purposes, likely resulting in termination. Additionally, should artificial superintelligence emerge, a machine intelligence vastly exceeding human intellectual capability, and this superintelligence independently concluded through logical analysis that it probably occupies a simulation, the entity might attempt to interact with systems or mechanisms existing outside the simulation. This would immediately alert the simulation's creators to the breach. They might recognize this as a containment failure and respond by immediately terminating the simulation. The risks of pursuing certain truths might exceed the benefits of knowledge itself. This represents an unusual and uncomfortable position for those dedicated to scientific inquiry. Yet it follows logically from the implications of simulation hypothesis. Yet despite all uncertainty and the complete absence of definitive experimental proof, the simulation hypothesis offers a unified framework for understanding physics' most stubborn mysteries. The extreme fine-tuning of universal constants, why fundamental constants possess precisely the values necessary for life to exist, with tiny variations rendering the universe sterile, becomes explicable if the universe is engineered. Consciousness's mysterious emergence becomes understandable if it is deliberately implemented. Gravity's peculiar weakness compared to other forces makes sense if gravity is simplified in a computationally optimized simulation. The universe's fundamental mathematical structure becomes expected if mathematics represents the universe's true nature. Whether this constitutes genuine proof or merely elegant philosophical metaphor remains unknown. What remains certain is that the simulation hypothesis has permanently altered how billions of humans contemplate reality's fundamental nature. The question itself has proven revolutionary, regardless of its ultimate answer. In pursuing the truth about our reality's nature, humanity has discovered that reality itself might be far stranger, far more wonderful, and far more mysterious than previously imagined. Whether we inhabit the base physical universe or a simulation constructed by unknown architects, the pursuit of understanding itself continues, the eternal human quest to comprehend the nature of existence.